Okay, so that's the velocity part of it. Let's talk briefly about the heat transfer part of it. So now we're going to start with our energy equation and derive what some people call the thermal law of the wall. It's the same thing, but instead of solving for a velocity profile in terms of inner coordinates, now it's a temperature profile in terms of inner coordinates. So we again start with our energy equation. We have our thermal conductivity. So there's our kind of modified Fourier's law, the thermal conductivity plus the thermal diffusivity or thermal eddy diffusivity term in that last piece there. And we want to figure out, can we throw away some things like we did with the velocity profile? So again, as we get really close to the wall, U becomes small, V becomes small because we're close to a wall. So this whole left-hand side goes away. Right? And that's again, assuming that d temperature, d time is 0. This is a steady solution. There's nothing, it's not like we're just starting the flow or there's anything changing with it. We're just assuming that that is going to 0. So if we throw that part away, we're left with the right-hand side, and that is just rewriting it here. We have d dy of minus k plus rho c epsilon h, which is our thermal eddy diffusivity, times d temperature dy, and that is equal to 0, right? That's the only thing that's left. It's equal to 0, at least approximately close to the wall. Okay, so that is saying then my apparent heat flux, dq dot double prime apparent. That apparent just means it's the averaged quantity. It's including the fact that you have these oscillations in time, but we're integrating over time and it just becomes an apparent heat flux. So apparent heat flux with respect to y is equal to 0. So the apparent heat flux is not changing as a function of position y here, which means that q dot double prime apparent is a constant. And we'll say that that's equal to the heat flux at the surface, q dot double prime s. Okay, then rewriting our equation, we have minus k plus rho c epsilon h dt bar dy is equal to q dot double prime s. Okay. We'll again use the same. So I'm not even giving you a different table here. This is exactly the same table. We will use this table for the temperature distributions, keeping in mind that epsilon sub h is equal to epsilon sub m divided by the turbulent Prandtl number. Right? And this turbulent Prandtl number is usually 0.91. I think I said 0.9 last time. It's usually 0.91. So unless you have reason to believe otherwise, that's what you use for that. So again, let's use the Prandtl-Taylor model just to keep it simple, consistent with what we just did. And let's go through and substitute in what we need to get to inner coordinates for this in order to use this model. All right, so I gave us a little head start here. Here's the version of the equation I just wrote out. And then our inner temperature is given by Ts minus T bar over T star, where T star is what? It's q dot double prime s divided by rho c u star. So we substitute that in and we get our inner temperature, and we have our inner position y from before. So let's see, let's bring this in here. We end up with q dot double prime s is equal to k plus rho c epsilon h times d theta. So now we have to figure out d theta plus dy plus. So we have to bring along all the constants that are multiplying those things. And those are c q dot double prime s over rho c u star times tau over, let's see, u star times mu. Okay, and let's, I guess, remember that, make a note up here. So u star we said was square root of tau s over rho. So let's see, we can get rid of a few things here. So U star. So we're going to take the square of, so we have U star times U star. So we'll take the square of that tau s over rho. And we end up with here Q dot double prime S is equal to K plus rho C epsilon H d theta plus dy plus. And then here, see, we cancel out. What are we canceling out here? Rho C. This is exactly what I just wrote. Not quite. Oh yeah, let's with the U star. Okay, so this is Q dot double prime S over rho C. Now we have tau S over mu and rho over tau S. Okay. Q dot double prime S goes away, so that's on both sides, so we can cancel that. Tau S goes away, so we can cancel that. Well, we have rho over rho, but let's leave that. Let's actually bring the rho C inside of the parentheses to get rid of rho C in front of the epsilon H. And doing that, we end up with 1 equals K over rho C is going to be alpha, our thermal diffusivity, plus epsilon H d theta plus dy plus times rho over mu, which is 1 over nu, our kinematic viscosity. Okay, a couple more steps. We can keep going with this. We can bring the nu inside to simplify things a little bit further. So we then have 1 is equal to alpha over nu. Alpha over nu is actually, so nu over alpha is the Prandtl number, molecular Prandtl. So this is 1 over molecular Prandtl number. And then we have epsilon H over nu, but let's introduce also that the definition of the turbulent Prandtl number. And when we do that, we end up with epsilon M over kinematic viscosity nu times 1 over the turbulent Prandtl number times d theta plus dy plus. Okay. So if we followed that, that is our equivalent version in inner coordinates for the differential equation we started with in the upper left-hand side. Yeah. Let's see. So T. Oh, wait. We have minus. Let's see. So I think, let's see. So we had minus T. Yeah, I think it's because it's TS minus T bar, and that ends up canceling that, or canceling out that minus sign. I think, yeah, I think that's what it was. Yeah. Other questions on that? Okay. Okay, so we have now this equivalent in inner coordinates. So let's use our Prandtl-Taylor model finally. What we're going to do is start with 4. I guess I actually left this in here, but this is what I would be writing out here. So, okay, so 4y plus is less than 11.5. We're going to substitute in our assumption that epsilon m over nu is equal to 0. And so we do that, and we end up with theta plus is equal to the Prandtl number, the molecular Prandtl number times the interposition y. Right. So again, that's saying, it's just like the momentum equation where we had u plus is equal to y plus, except now for the thermal consideration, of course, the thermal is going to be related to the momentum by the Prandtl number. And that's what we see here. It's scaling it by the Prandtl number, the molecular Prandtl number. It's exactly what we would expect in this situation. Okay, so then the other part is for y plus greater than 11.5. Substitute this in. So now we have, this kind of gets a little bit messy, but we have 1 is equal to, let's see, 1 over the Prandtl number, plus, this is now kappa times y plus minus 1 times 1 over the turbulent Prandtl number times d theta plus dy plus. You see what I did there? I just took our model and substituted it into that equation in the bottom. So we have to now figure out how to do this integral. Let's first separate it out. So we'll say d theta plus is equal to, on the other side, then we have dy plus divided by all that stuff, which was 1 over Prandtl plus kappa y plus minus 1 times 1 over Prandtl turbulent. Right, so that's an integral that we can do, except that it's a little bit messy. We have y plus in the denominator, and it's part of that whole mess of stuff. So let's make our lives a little easier and introduce something. Let's introduce a new variable. We'll call it w. Okay, and w is going to be defined as, where is that here? So w is going to be defined as just the argument there. So it's 1 over Prandtl plus kappa y plus minus 1 times 1 over Prandtl turbulent. Okay. So then let's see, dw, we're going to have to use the derivative of that. So dw is going to be kappa over Prandtl turbulent times dy plus. So we substitute everything back in, that definition back in up there, and we get this equation. So I'll leave myself, I'm going to bring it over here. So we get what? We get theta plus minus Prandtl times 11.5 is equal to the integral. So we'll come back to what that is, but it's then dw over w times the Prandtl turbulent over kappa. So what are the limits on this integral going to be? Right, I already did the integral on the left-hand side from 11.5. So what are the limits on that? We have to do the limits in terms of w. So we actually want to use our definition of w, which is this. It's 1 over the Prandtl number plus kappa times 11.5 minus 1 times 1 over Prandtl turbulent. Hopefully you can see that. So 1 over Prandtl, kappa evaluated at 11.5 minus 1 times 1 over the Prandtl turbulent. That's our w in the lower bound of the integral. On the upper bound of the integral, that's just going to be 1 over Prandtl plus kappa times y plus, right? We're going to y plus minus 1 times 1 over Prandtl turbulent. Okay, so we do all that. Do that integral. You could probably use, maple if you're not sure of yourself. It's really not that hard to do, but we end up with theta plus is equal to Prandtl times 11.5 plus Prandtl turbulent divided by kappa times, running out of room here, I'll just go into this. So it's all this times the natural log of this whole big mess, which is 1 over Prandtl plus kappa y plus minus 1 times 1 over Prandtl turbulent divided by the lower bound, which is 1 over Prandtl plus kappa at 11.5. Kappa times 11.5 minus 1 times 1 over Prandtl turbulent. Okay. Hopefully everybody can read that. So everything in there it looks like a K is a kappa, right? We have Prandtl, molecular Prandtl here. We have turbulent Prandtl there. And this is our expression for temperature profile in this region beyond 11.5. And again, if you went back and used a different model, that's not the Prandtl-Taylor, this is going to look different from this, right? You're using a different assumed apparent heat flux. So because we assumed a certain form, we're just going through and solving that form. And it's tedious and annoying here, but we end up with a temperature profile. So let's look at what that temperature profile is. Okay, so here we have, again, on a log-log plot, we're looking at inner position, y, and inner temperature, that theta plus. We end up with the temperature profile. And what you'll notice right away is that this is now in terms of a Prandtl number, the Prandtl number being the molecular Prandtl number. And you see that, yeah, as a function of position, we're starting with, well, this kind of exponential looking curve is actually a linear, because we're plotting this in log-log. This is actually a linear temperature increase in proportion to the Prandtl number. And then once you get out into that region beyond 11.5, now we have this, what looks linear, but then is actually like a logarithmic distribution in reality. So you have these different temperature profiles, and really what's different between them is, once you get out here, the slope is the same, right? There's no real sensitivity to the Prandtl number out in that region beyond 11.5. What's happening is in this inner part here, that's really governed, the heat transfer is really governed only by the conductivity, right? The molecular conductivity right next to the wall. So if you're changing the Prandtl number, you increase the Prandtl number, you're making it harder for heat to flow across that really thin layer right next to the wall. You're going to see a larger temperature rise, right? For a given apparent heat flux, you're going to see a larger temperature rise. And that's what you see. So once you get out to this transition region, now you no longer are governed by that molecular conductivity, and things go back to really being dominated by the eddies. So that's what we see there. And if you plot this in normal coordinates, yeah, you see right next to the wall, there's a really big dependence on the Prandtl number, where the molecular properties really are driving what's happening. You get out, and then there's a really insensitive temperature profile to the position. So this kind of reinforces, I think, what we've been assuming about the temperature profile. When we sketch it out in the turbulent region, you see that there's a really steep gradient, and then in the wake region, there's really not much going on in terms of average temperature, but this hopefully gives you a tool set to deal with solving for temperatures and velocity profiles in turbulent flows directly, where previously we just sort of waved our hands at it.